Okay, let's continue from where we stopped last time. So this is simplified further. This left or right side here. Let us simplify it. So this is Fy. Uy is Fy over k. So this becomes 2k. And then plus Fy. Okay. U mu is mu uy minus uy. Okay. So this part here becomes mu minus 1. So this will become Fy uy. Okay. But uy is Fy over k. So this becomes Fy over k times mu minus 1. Okay. So this mu minus 1 is multiplied by 2. If I multiply this by 2 here, I have to divide it by 2 such that this will be a common denominator to be inserted here. So what we are deriving at is only this 2 mu minus 1. Okay. So since this is now 2, and we factor out Fy squared, so this 2 will be multiplied to a mu there and a minus y here, but the LCD is still okay. So Fy squared over 2k plus Fy squared over 2k also. Okay, but you have a 2 there. So if I take out, if I insert this here, so I will have to put okay, 2 mu minus 2 there. Okay, and then of course we have to factor out Fy squared over 2k. Okay, this is 1 plus 2 mu minus 2. So this will now be 1 minus 2 becomes 2 mu minus 1. So this will be okay inserted there. So consequently your correction factor now becomes square root of 2 mu minus 1 for the acceleration. Okay, so this is used for the acceleration. Okay, so let's take a look now on the other reduction factor. This is now actually seen on figures 5.18 and 5.19. So this reduction factor is actually applied on this tripartite design spectra, which is normalized to 1G, and this is undamped. Of course, There's no damping here, but the mu factors are there. And here, this is already a 5% damping, and the mu factors are also there. Okay. Okay, for this part here, there's a note for both figures that the spectral values SA and acceleration SV and velocity SV are directly obtained from the graph, but for ST, the displacement must be multiplied or amplified by the ductility ratio mu. Okay? So, hindi pa siya carried dito no, sa normalization. So, let's take a look at the illustrative design example. We calculate the response of the single degree of freedom system of example 5.1, assuming that the structure is designed to withstand seismic motion with an elastoplastic behavior having a ductility ratio mu equals 4, assuming damping equal to 10% of the critical damping. And for letter A, we use the response spectra of the L-center earthquake, and for letter B, we use the design response spectra. Okay. Okay, for solution of A, given is the period t equals 1 second, the same as example 5.1, 10% damping, and mu equals 4. So we use figure 5.15 for this spectral graph, which is not yet normalized. I think this is okay. This is 5.15. So if we are going to take a look at your ductility factor, this is 4 on the graph. Here's the ductility factor, and the period is 1. So we can set actually your point somewhere here. Okay. So let me check my battery first. Okay, so for the spectral displacement, we can plot the displacement which is exactly here on this graph. So more or less it's actually 1 inch. So let us check your answer here. So this is 1 inch. Okay, so this is more or less okay. Then multiplied by mu, it's 4 inches. So for SB, okay, for the velocity SB, so we can look into this vertical axis somewhere at 5, 6. Okay, slightly greater than 6 or almost 6. And for the acceleration, it's 0.1 of g. Okay, so we can take a look on that answer. Okay, so 6. Okay, so it's quite okay, and 0.1 of g. So for letter B, we use the figure 5.20 corresponding to 1 CPS, we obtain the following maximum values for the response, and the scale factor for G is 0.32. So since this is a normalized graph, we use a scale factor. So this is, I think, the graph 5.20. I think 18, 19, 5.20. So I don't have the 5.20 here.